Same as the previous episode, I recommend you to download the PDF file of this mind map, and then you can go through that with me together. And in this video, I'll show you my thinking process and also how I sequence them together. So let's start with the word wave. And then the sequence that I'm going now may not necessarily be the way that you learn through this chapter. I would like to start with traveling waves, okay, and standing wave. And if you finish the whole chapter, standing wave is something that we come across later on. But the very beginning time when you learn about waves should be traveling waves, which underlying there will be two more category, which is transverse wave and longitudinal wave. For transverse wave, we have some examples, like one big essential example is the EM wave, which you also find in the data booklet, that we have the corresponding order of magnitude of wavelength, and which you can then work out the frequency if you need to. But it's important to know that you have this in your data booklet. And then we also, in the transverse wave, we have mechanical waves, and one kind of them is a string wave, like how you normally see just simply swinging a rope or whatsoever. Then you can create a pulse or a wave. That's a transverse wave. And then for longitudinal wave, in fact, you can also, if you use a slinky, you can also create either the transverse or longitudinal. But to be more specific, I guess it's probably easier to talk about sound wave, which is a longitudinal wave. And for mechanical waves, they all rely on oscillation of particles, while EM wave would be relying on the oscillation of E and M. That's why electric and magnetic field. And that's why EM wave is so special, where later on when you learn about maybe special relativity and other stuff, light, which is EM wave, that is the only thing that can go through vacuum. While for other waves, it really requires a certain particle medium. So that make something very special for EM wave. Now, going back to the more fundamental idea, we'll come back to standing wave later on. But when we try to describe a wave, okay, this is how physics is, right? If you remember earlier, we talked about how we can describe a motion and therefore coming up with displacement, velocity, acceleration, etc. So here's the same idea. We want to characterize them. For the wave, we have wavelength, frequency, period, amplitude, and wave speed, how fast they are traveling. And so one of them, the time period, has a relationship with the frequency in this relationship, okay, inverse of each other. And then we can also describe by simply velocity equals to displacement over time to derive the formula of V equals to F lambda. Okay, I'm sure you all know that. And then in terms of the drawing, to visualize the wave, we can apparently you should know how to draw a different kind of wave, but then you have to be aware of the word, which is a wavefront. So normally the one you draw, like people call it the Wi-Fi shape pattern for circular wave, then that's called the wavefront. Okay, and in terms of the direction of traveling, that's called the rate, and they are perpendicular to each other mathematically. Okay, and then before I move on to SHM, I would like to address that you are expected to understand how to or read the graphs of both transverse wave and longitudinal wave. Okay, they are both traveling waves, of course. In terms of displacement position graph, so for displacement position graph, it simply looks like how the waveform look like. Okay, transverse wave would be something like that. And then displacement position for longitudinal would be something more complicated. Okay, but essentially it still look like a longitudinal wave. Okay, it's just the particle will get compressed or more separated, which is the rarefaction you can find. As for the displacement time graph, remember that whenever you see displacement time graph, it has to be describing one particle only. Okay, that along maybe is one of the particle in the medium. So for example, in the transverse wave, it would be one particle of the string, or maybe in a longitudinal wave, for a sound wave, it could be a displacement time graph of an air particle, okay, which is having the sound wave passing through. So the reason why we have to do these two graphs is because of we are describing, and then you can then identify different things. You can think about how we can get the wavelength, frequency, period, amplitude, or even speed from these two graphs. Okay, they are quite unique, okay, to each other, and then they could give out different information among these fundamental quantities in wave. And now moving on to the next point, and because of especially displacement time graph, like I said, they are in fact, when they oscillate, they are also moving in a periodic cycle, and that's how this arrow is so important, that it link to the idea of simple harmonic motion. And that's why when you were maybe at the very beginning learning about simple harmonic motion, it looks like a mechanics topic, but they now put it into a wave topic, because basically this is how they come hand in hand together. Because the oscillation of the particle basically is a mechanical oscillation motion. So now we'll come to the world of the SHM and onwards. So first, we would have to talk about the definition of SHM, which is this one, A proportional to negative x. But to make it more direct, then it will be with the omega square as a coefficient. You have this in a data booklet. And with this very special relationship mathematically, we have a consequence of all these things. And I believe in your experiment in school or simulation, you will be able to find that. First, the amplitude does not affect the period. Second, in SHM, we assume there's no energy loss, and therefore the amplitude remain the same. Unlike later on you encounter the damped motion, the amplitude will decrease. Number 3 is the restoring force nature. Okay, and this is basically how A is proportional to negative x. So when x is going on to, say, to the right, then the acceleration, which is directed by the force as well, is pointing to the left. So they are always opposite in direction, but proportional in magnitude. So this is the very interesting features about it. And so coming back to the quantity of angular velocity, because you have omega here, then don't forget, in circular motion you learn about it. Again, you have this relationship in your data booklet. Now, I would like to stay with SL, okay, as much as I can. With SHM examples we encounter in IB Physics, we have 2 examples. The very usual one would be this mass spring system, where it's a very simple mass and then hang it with a spring and then mass, and then you'll be able to derive the relationship of the period, which is this one. Again, you have this equation in data booklet, but if you really want to derive it, then it's quite simple. It's just really just Hooke's law, negative kx equals to ma, and then you can have the derivation. You can look at the video if you want to look at for more details. As for the other system that will also be included, will be the simple pendulum. However, you have to be aware of the assumption that it only works with small angle, because in the derivation, which you may have skipped when you're learning it, but one essential technique you need is small angle approximation. So then we can arrive this time period equation. Otherwise, with an angle that's too large, say more than 10 degree as the amplitude, then you cannot reach very closely to this equation. All right, and then we could also look at how later on we have the damped motion and resonance. So first thing is, in fact, these 2 equations are very helpful whenever you talk about natural frequency, because natural frequency is simply how an object or a system would oscillate in a certain frequency, okay, when it is set it off to move by itself. And so then you can describe the natural frequency of a pendulum or of a mass spring system using these two equations. So wherever you calculate as t will be the period, and then you convert with t equals to 1 over f, which we just talked about here. You can then find the natural frequency. And natural frequency is something that you need when you talk about resonance. If the driving frequency is very close to the natural frequency, then resonance will happen. And resonance, I'm sure you all know, it will basically give an effect to the amplitude of the oscillation, so it go quick, like more and more and more. So example could be like this. I'm not going to read through it, you can refer to it by yourself. I believe this is something that I copy from the subject guide, so you may want to just make sure you at least you understand what that means. And then a diagram could be shown here to illustrate how the ratio between the frequency, natural frequency and driving frequency, will affect the amplitude. Okay, you may not need to know the exact label here, okay, because this is really on a very special circumstances, but I think overall the shape, okay, you can understand like that. When the ratio is equal to 1, because they are close together, then the amplitude basically skyrocket. Okay, and so that's one side of the story. Okay, when you have a driving frequency. On another side of story, you can also have a damping force. Okay, so something different is for driving force is always in a constant direction. Okay, disregard of how the object is moving. While damping force, you have to be, you have to understand the difference is that it's always opposing your motion. Okay, so it will change direction according to your velocity. And that's why it's called the resistive force here. And in different amounts of resistive force, they would then be categorized into 3 cases: the light, critical, and heavy damping. You may encounter the word over dam, under dam. I guess it's quite straightforward that you can understand how they are equivalent in words to each other. But then you have to understand this diagram. Okay, for under dam, basically you can see the amplitude decrease, but it takes a really long time to decrease. Over dam means that it doesn't really oscillate anymore, but the amplitude still decrease super slowly. While for critical dam is like the quickest way. Okay, so then it doesn't oscillate, and then it gets the shortest time to stop. Again, either the damping or the resonance case, they both are affecting the amplitude of oscillation. So that's something that are in common. Oh, sorry, I forgot to mention about the energy. So in terms of SHM, going back a bit more, if you are SL only, then you are expected to know and describe how the energy are interchanging qualitatively. Okay, and then the graph will be like this. Okay, I think it should be quite straightforward. And I guess we could go for the HL part if you don't mind. Okay, because I think it's really important to finish this part up for the HL. So going a bit more for HL student, then you learn more about the quantitative description or expression of how the displacement, velocity, and acceleration, etc., could relate to each other. And because of the motion itself is basically a sine curve, then we can model it using this equation. This is what you have in your data booklet, so I will recommend you start with this. If you read other textbooks, they may start with cosine. In fact, it doesn't matter. It's really just about the phase difference. Find the symbol here, which is also something that you need to know as well. And with this equation, you can differentiate if you know calculus, and you can arrive the expression of V. And interestingly, with this phase difference, we can then observe how displacement will be leading the velocity by 90 degree. As you could see, it was sine and then become cosine, and then if you differentiate again and it become negative sine, and therefore velocity would lead acceleration with also 90 degree. And overall, if you compare displacement and acceleration, then the phase lag or phase angle will be 180 degree because you just add them up together. And that's how the negative coming from. If you go back and think about how a is proportional to negative x. In terms of the diagram, this is a nice diagram I find on Google. So you can pause the video if you want to and try to see how they are really offset by a quarter of the period, which is 90 degree. Okay, you can change it to radian if you want to. So one cycle is 2 pi, and therefore 90 degree will be pi over 2. Now, going on to the energy part, if you're HL, then you also need to know quantitatively. And so we have an equation like this one in the data booklet. I will recommend you to understand how we can arrive this. This is the potential energy, obviously the elastic potential energy for the spring mass system. And therefore, to arrive this equation, we basically are looking at one of the equation we have, which is from the mechanics, the elastic potential energy equation, half kx squared. The thing is with k, they just change it to m omega square. So that's why I put up this equation here. I don't think you have to know it particularly, and this is also not available in the data booklet. I just want to show you how it come together. So it basically, you can take this equation from the period, and then you can also come with the omega equation. You put them together, and then you'll be able to reach to this expression, and then you plug the k back to the elastic potential energy equation. Then basically you can then find this half k squared, and then the k become m omega squared. Okay, so obviously the omega should stay constant within a certain SHM, so it's only about the position of the mass where it is affecting the potential energy, which should make sense to you. As for the total energy, if you understand the qualitative idea, then basically when the potential is at maximum, that would equal to the total energy, and that's why the equation basically is the same as potential, except that x is now x log. X log means the amplitude. And using this equation, you can then also find the expression of kinetic energy, and then you can then rearrange it and then arrive to this last equation about velocity in the data booklet. Okay, it's just a pretty interesting way you can just derive it yourself if you need to. But as for handling maybe exam question, then you probably just want to see what information you have and just find the most convenient equation to use. One more thing to perhaps I can add here is that if you can observe the equation here, which is say x equal to x log sine function, then you should always recall x log is the amplitude, while for v equals to omega x log cosine function, remember the cosine maximum can only be equal to 1. In most of the other time could just be maybe 0 or 0 point something. So the maximum of v, which you can notate it as v log, should equal to omega x log. And same for acceleration. Acceleration would be the same idea as using this equation, a log equals to omega square x log. So this is how you could figure out the magnitude of the peak value of x, v, and a. Now we are done with SHM, then let's go back to a more fundamental idea. I would like to talk about the wave phenomena, and you probably have seen the demonstration of how the wave can overlap each other, and one of the very easy and simple idea and as a principle is called the superposition of wave, or principle of superposition, which can tell you what you may expect in terms of the amplitude when two waves are overlapping each other. And And because of this so simple but important principle, then we can then have something called the standing wave, okay, forming, and also the idea of interference later on. Okay, we'll come back to this one later. We have something that so fundamental and so interesting called the Huygens principle, and if you're interested you can search online, but as you can see I indicated as gray and is not required in our IB syllabus. Basically is considering the wavefront. As you remember just now we talked about wavefront, is consists of a series of circular wave. Okay, again, if you search online you'll figure out some animation, and it's quite mind-blowing. And so with that in mind, then we can have property like as simplest one is will be reflection, refraction. You probably have learned way earlier, and then in IB you learn about diffraction and interference later on. And in fact, it's all can be explained by Huygens principle together with superpositions of wave. So perhaps we go for reflection first. Reflection, there are two kinds mainly in IB physics. One is you can consider a rope, okay, like the diagram here. And so it will basically bounce back, but it depends on the boundary condition, okay, whether or not it's a fixed end or a free end. So what you have to bear in mind is that if it's a fixed, or we can call it closed end, it's just a wording thing, then they will have a pi phase change. Okay, pi phase change means literally inverted, as you can see in this diagram. While for free or open end, okay, it will just more like continue moving, but just changing the horizontal direction. If you're wondering why this is the case, in fact, this can easily be explained by Newton's third law. Okay, so that's the 1D case. As for 2D case, then you probably have seen things like a laser pointer shining onto a mirror, plane mirror, and then reflect, and that is the reflection law, which is incident equal to reflected angle. Now moving forward to the next phenomena, usually school would talk about refraction, and we have refractive index. This is a definition how speed of light in vacuum over the speed of light in that particular medium. For example, water, refractive index is 1.33. So according to this, then the light will travel slower in water. If you really want to dig deep down to why is the case, why would suddenly the light be slower, in fact is a very complicated concept. I'm sure you can find a lot of very interesting video on YouTube, so go ahead if you want to, but in fact it could be best explained by something called principle of least action. Okay, something is really interesting. But that's not in our syllabus, okay, but so feel free to explore it yourself. So either way, because of this, then we have Snell's law, which can be described mathematically, okay, due to the refractive index and also the angle, incident and refracted angle. And then very special circumstances may arrive called the total internal reflection when you are going from a slow medium to a fast medium. This is not a proper word, okay? The proper word should be optically dense and optically less dense, but that I'm just trying to give you an idea. And then if you are able to have that, then at a certain angle, which is called the critical angle, then you can have the refracted angle to be 90 degree. Okay, so as you can see here, literally is 90 degree. Okay, and beyond that, the refraction basically is gone. Okay, so you can only find the reflection. Okay, 100% reflection. Before that, in fact, there's also reflection, but it's usually negated. Okay, so that's about total internal reflection. Now, moving on to diffraction, something that for the SL student, I mean everyone's to easily recall as a rule of thumb. is you should expect there's a strong diffraction pattern occur when the slit size, as you can see, there's an aperture having a wave trying to get through it, and then that's how the wave spread out. Okay, that's called diffraction. And so it's actually relative. The size of the slit and then the wavelength is always relative. And so it will be strong, considered to be strong when the ratio is close to 1. So that's something you could consider. The symbol is B and lambda. And we'll come back to this again later on for the HL regarding the single slit diffraction. Now going back a little bit to interference. So as we said, when wave or even pulse overlapped, then there will be superposition, and when things get more systematically, in fact, we will call it interference. In fact, they are the same thing. It's just that it get 2D and then it get more systematically analyzed, it become interference. So the premises of interference in IB physics is they expect it's a coherent sources. So that will mean that the frequency and also the phase are the same. So that is always coming, having a certain point to be constructive interference, and then maybe another point to be destructive interference, always. You can imagine that if the frequency is not even matching, then you will have very inconsistent interference happening throughout a certain duration of time. So you should expect the word coherent as a requirement. Okay, same frequency and constant phase angle. Okay, you can have phase angle, but it's a constant phase angle between two sources. So that's why the idea, in fact, are so interconnected together in terms of the phase. So coming back to here, then we could then derive a relationship that's having constructive interference, and when the path difference is n equal to n lambda, n being an integer, so 0, 1, 2, 3, 4 onwards. While destructive is when the path difference equal to, say, 0.5 lambda, 1.5 lambda, 2.5 lambda, and so on. Okay, path difference is really just how the two sources versus a point. Okay, source 1 to the observer, and then source 2 to the observer, that two distance difference. Okay, path difference. Okay, go and check out the practices if you are not sure what I mean. And so the word nodes and anti-nodes will come to you by considering at that particular point, do they have constructive or destructive? If it is constructive, it's called anti-node. Okay, because node is like a knot, basically. It's not moving. Okay, so node is destructive, anti-node is constructive. Constructive means it's always having a great changes in the movement. Okay, and so putting that into a more specific case, because you can use this interference idea into many different situations like sound wave, water wave, but then Thomas Young basically put it into light as an experiment. So that's why Young double slit experiment. And then there's an equation you can derive. I'm not going to go through the derivation. You can find it in the textbook. Basically, it's the same how you can make use of the path difference, and eventually you reach this. So that's the equation you need. As for the quantity, I guess we'll have another video on the whole data booklet, so I'm not going to describe it in very detail. Now going back, okay, and stay within the SL area, we have to go back and talk about standing wave. And so the formation of standing wave is actually very often asked, and there are some words that you need would be the word superposition of wave. And so imagine how its form is literally like you have a wave going through to one side, and then it will be reflected, but remember it's not just one pulse, and maybe there's a continuous wave. So the incoming incident wave and then the reflected one will meet each other, and especially the reflected one will also have a phase change probably. Then they would be forming a certain pattern, and with the right frequency, then a standing wave can be formed. And that's why we talk about the first harmonic. It has to be a very specific frequency. And I suppose if you have gone through that or watched my video, you find out there are first harmonic, second, third, and so on. Okay, that's basically infinite. So you need to know how to draw them. And you also need to be aware there are cases, three different cases. So the diagram here, I don't want to put up everything. This is just with two ends fixed. There are also cases where two ends are opened, okay, which is three. But they are basically essentially the same mathematically. The other case is rather special, which is having one side fixed, one side to be free, or one open, one closed case. Because when we look at how the different harmonics having different frequency, an interesting idea, a very elegant result would be fine, which can be, you can see here, is multiply an integer of n of the first harmonic. But then we cannot find, if you try to ever draw it before, then you will find out for one open, one closed case, it's just an odd number. Okay, while for two open, two closed will be just the whole series, 1, 2, 3, 4, 5. Okay, and that should basically describe all sort of standing wave pattern in string, like string instrument and pipes. Okay, these are the wording from the subject guide, and that's why I copy here. Now, the very core idea, okay, these are just fundamental idea, but then another like stage higher concept is how you can compare the standing wave with traveling waves. So this is a list which you can take note of. So as for standing wave, okay, this is from the standing wave perspective, they do not transfer energy. The energy is stored in the system, so they do have energy when they are oscillating. Okay, of course, I mean they are moving, right? Versus a flat line, then of course there's some energy, but they're not transferring from one position to another position, unlike the traveling wave. Second point, it appears to be stationary, of course, with the fixed node and antinode, which they have zero amplitude, and the antinode has a maximum amplitude. And do pay attention that means for the I mean this is a node, and then in the middle is antinode, but between them, although we don't have name for them, they also have amplitude, and interestingly the amplitude is changing. Okay, so from 0 to maximum in the middle is like gradually changing, which basically is the third point. And then lastly, you have to think about the phase. Okay, I find it a bit strange, honestly, that you SL student are expected to know this, but then I think only the HL student earlier in SHM need to know phase angle. So for the best SL, if you're SL, I would still recommend you understand the idea of phase. So basically, you in this case, very especially, you need to say look at the third harmonic. You should expect something like this. Okay, I'll try my best to draw. Okay, yep. Okay, so at one instant, okay, it will be like this for the string. And so you can see that for this particular part, okay, all the particles will be going through SHM. If you think about individually, it's SHM, except that they have different amplitude, but then their frequency are all the same, and also their phase are all the same. They will get to the peak together, they will get to the middle that together, they will go to the trough that together. They are always in phase. While for the next half of the cycle, you can essentially see that they are opposite. Okay, so although within this green circle, all the particles are in phase, but then the yellow one that I circle here and the green one, they are always be out of phase. Out of phase means that they are of a phase difference of pi or 180 degree. And so I think this is something that people, or I mean students, always overlook, or they didn't bother to just think through it. It's not very difficult. Okay, you just have to imagine it in your mind. Now let's talk about the HL part. Okay, for a while, we talk about double slit, and then in HL we also got first the single slit diffraction, and then we have an equation describing that. I mean, although I really should save it for the data bullet video, but I just want to emphasize that pay attention to the symbol B and then the symbol D. They are different. Okay, you can find it out by yourself. And then as for the angle here is the first minimum. Okay, people always for some reason thought it's the maximum, but it's not. It's the first minimum. So when you apply this equation, just you have to make sure you understand how they are defined. So the single slit diffraction effect will give the envelope, or we use the word modulation, which we'll lately go through that. Maybe I'll just show it to you now. You know, the red one, okay, is the double slit pattern, which therefore the bright and dark fringes. And then the blue one is a so-called single slit envelope, okay, the modulation of the amplitude. And so the first minimum that we're looking at will be something like around here, okay, around 20 or maybe 18 degree in this diagram. Okay, and then that's basically how it works. And then now we can then move on to an idea of multiple slits. And multiple slits could be of any numbers, basically 4, 6, and 20 that in the diagram that I included here. And so if you ever try to observe them, then you find something really special, and that is for the nth slit cases, then the intensity will be proportional to the n square. So the idea is very simple, that if you have 2 slits, then basically amplitude at the central maximum will be 2a. Imagine the original is a. And then for 4 slits, because there are 4 sources, then in the central maximum, the amplitude will be 4 times. So 4a. But the thing is, this is intensity. So with the equation that intensity proportional to the amplitude square, then it will become 16 times. So that's why it's always square. So in the 6 slits case, it will be 36. And then 20 slits case will be 400. Okay, if the original intensity is 1. Okay, it's a relative intensity here in the diagram. Secondly, you'll find out the maxima become thinner and sharper as you go down. Okay, you can see it's more like pointy and sharp. And then the secondary maxima is gone. Okay, these are the original secondary maxima. The idea is, again, very simple if you consider the conservation of energy, because I mean this is 400, okay, times higher. So I mean the input light laser, for example, didn't change, right? You probably just swap the different slits. And so as a compromise, if this is so high energy, then the other part, okay, of the output has to be much smaller. So that's why it's sharper and thinner. All right, so that's the idea. And then if you try to put the idea forward as a diffraction grating, and then you have this equation, and then the diagram will look even sharper. And also if the slit width is small, then the first single slit effect for the first minima will also be very far from the central, and therefore the idea of diffraction grating will be very useful for observation. Now the very last part of the wave will be the Doppler effect under the wave phenomena, because it only can happen for wave, not particles, obviously. So the very first equation you learn for everyone is this equation, which I don't quite like it in this syllabus. In the old syllabus it wasn't like that, but I guess I'll just have to go with that. Just pay attention that this equation is an approximation, it's not the full equation for Doppler effect. The better equation actually happened in HL. Okay, unfortunately, I don't know why they do it like that. Anyway, so when you are using this equation, you have to make sure that if you are having a scenario working with light or EM wave as the wave itself, then of course the speed is the speed of light c. Okay, then you can, yes, use this equation. When it's involving like the observer or the source moving at a speed much lower. Okay, so basically you don't, in the case where you don't have to consider relativity. then you can use it. However, this equation can also be applied to a non-light speed case. Okay, for example, when you talk about the speed of sound, and for example, a person walking, for example, then the speed of sound is much faster still compared to the observer or the source, okay, whoever, like which one it is. So when you substitute a speed of sound in this equation for that case, then C will be the speed of sound, and then the V will be probably the observer or the source moving. Okay, so you can still use this equation in this case. Of course, for light, then will be even more straightforward. And because of this equation, we can then observe a change in frequency or wavelength for the light coming from the planet or stars. And therefore, we can then find the shifts in the spectral lines. If you don't know what that means, it's something that we will learn in topic E, okay, about the emission spectrum. Okay, if you haven't got that, then that's fine. Okay, but if you already finished the whole syllabus, then you should know this from topic E. And because from our observation, the evidence are always showing a red shift, and that will means that the planets or stars, other things are always moving away from us, no matter which direction we are observing. So very interesting observation, and the only explanation that we can explain why everything is moving away from us is the universe is expanding. So that's the evidence we have to support this idea. As for the SL remaining part is how you can understand the drawing. It would be for the cases when the source is moving and when the observer is moving. So when the source is moving, you can see that this part, if the source is moving to the right, then the wave is more like being compressed. Okay, while on the other side is the other way around, it's more like stretch apart. While for the observer moving case, in fact, the waveform doesn't change. Okay, imagine the car is just here, okay, having its on, making a sound, and someone is running by. The waveform is exactly the same as it was. It's just the way that it perceived by the person X and Y here will be different depending on their relative speed to the wave. And so for the HL student, then you can then derive this more standard Doppler effect formula for the moving source and moving observer cases. And the way that you can derive it is by understanding that when the source is moving, the wavelength change. I mean, come on, it's very obvious, the wavelength change. But the velocity does not, okay? The wave still coming to you as how it normally is, perhaps 330 meters per second. So with that, then you can deduce the first equation. For the observer moving case, then you need to be aware that the wavelength does not change, as you can see from just the diagram. I mean, come on, the wavelength didn't change. However, as I said, the relative velocity change because the observer X and Y here are moving. So it's not 330 meters per second for the wave anymore. It has to go on with an addition using classical physics. And therefore, the velocity would now be a new velocity. And then after the derivation, you can find these two equations. IB subject guy said you won't be given a case where it will be combined, but I would say that if you really encounter that, then you can still combine the equation. It shouldn't be too difficult. And therefore, you may be asked in different applications, so other than just how maybe a very general case of so-called a source and observer, they can be used as a radar by manipulating the effect of Doppler effect or medical physics. So basically, they are making measurement. For example, a speed meter of a police car then detect how fast a car can move by sending a wave to the car, and then that car reflecting a wave back to the sensor, and then by measuring the shift using these two equations, then you can then identify that object's moving speed. Similar in medical physics, then you can also measure, for example, the red blood cell using ultrasound by measuring the shift in the frequency. All right, and I think that's it for the whole topic C. Stay tuned for the next one.